In this presentation, we're going to look at proof with truth tables. So I'm going to go to this first slide here, and what we're going to do is have a quick review of all the operations that are involved in logical truth tables. We have the negations there, and what we're going to do is fill those ones in first off. So the negation of p, or not p in other words, is essentially what we do there is transpose any value from 0 to 1 or 1 to 0. So in the first row there, p is equal to 0. That means the negation of p is 1. In the second row, the value of p is 0 also, so the negation is 1 as well. The same thing works for q. If q is 0, the negation of q is 1, and if q is 1, the negation of q is 0. So that's a quick reminder of what of negations, or the not operations. What we're going to do now is look at the and or operations here, and so let's fill in the truth table there again. So it's essentially the and or, so we do both together. And means that p and q both have to be 1 for the p and q to be 1. Otherwise, they are 0. So in the first row, we have p and q. That's 0 and 0, so that's a 0. In the second and third, there's only one. One of them is 1. Only one of them is true. So in that case, we'll have a 0 also. Both p and q have to be true for this to be 1. True as well. It is not so. That's a little typo there. It's not so. So rigid. So for P or Q, what we have to have is that at least one of P or Q, at least one of them is true. So there only has to be one of them equal to 1. In this case, we have Q is equal to 0, P is equal to 0. That gives us 0 there. But elsewhere, we have a true state somewhere. We have a 1 somewhere, so that means we have 1s here for the rest of them. Okay, so moving on, we're going to look at the conditionals. Again, I'm just going to talk about the truth tables there. These conditional biconditional, unconditional, and implication connectives. The logic of why they are 1 and 0 is a bit hard to explain in a presentation, a quick presentation like this. So I'm just going to sort of state that for the record that those are the values there of the truth tables. And I'm finally going to go on to the last one, the XOR, the exclusive OR. Exclusive OR means at least one of P or Q, of at least one of them has to be true, but not both of them. So it's very similar to it's very similar to the OR. Just for the difference is that when P or Q are both true, P and Q are both true, the OR value there is 1. But for exclusive OR, it's going to be 0. Only one of them can be true. So we only are allowed to have 1 0, or a 0 and a 1 for P and Q. We can't have them both the same. Now, what we're going to do quickly is use truth tables to prove this following expression here. So P and Q, or not P and not Q, is equal to the biconditional for P and Q. So I'm going to just quickly set up the truth table there again. It's something very similar to what we've seen already. P and Q there on the left hand side, not P and not Q, just to the left of center, and on the far right we have the biconditional of P and Q, and those are the values we've seen previously. So what we're going to do is just column by column. We are going to look at the first one, P or Q, which is the first phrase here, up in this truth table here. So what we're going to do is open that logical expression, is just input in P or Q, P and Q, and so we have 0, 0, 0, and 1. We're going to do something very similar now for not P and not Q. It's just essentially the same operation, but the not P and not Q, the 1 and the 1 are in a different location. in the first row. So we have 1 here, 1 here. That means we have our AND value here is 1 also. Elsewhere we have zeros. Okay, we're going to have the union of these two. So we're actually have this part here first, this part here second. Now we are going to put in the OR statement for both of those components. Essentially what we have here, if at least one of them is 1, those pairings, 0 and 1, that means we have a 1. If both of them are 0, that means we have a 0. So in the first row we have 0 and 1, that gives us a 1 here. 0, 0, 0, 0, that means we have 0 here and a 0 here. We have a 1 here and a 0 here, so down here we have a 1. So this is the full this is the full statement on the left hand side of that logical expression. What it remains for us to do is just to point out that both of them are directly equivalent to each other. We actually have the same membership table values for both, so that means we can sort of make this statement up here, up at the top of the page, that the P and Q, or P not P and Q, not Q, is directly equivalent to this biconditional of P and Q. And that ends our presentation.